Hello everyone, welcome to the Pacman contest. I'm Junaid Rasool representing team The Masters. Let's meet the team first. As you're already aware of the rules of the game, in this video we'll be explaining the approaches we have taken, its implementation, the challenges faced, and how we could have improved our game. So starting with the techniques, we chose to go with 3 different approaches to design our agents: the value iteration process, the enforced hill climbing, and queue learning. To give you more on the design and the implementation, let's go to the other members.
Hello, my name is Jay, and I worked on the queue learning agent in our implementation. The queue learning agent was designed as an offensive agent with defensive qualities in a variety of scenarios. The approximate queue function was used by creating a feature vector and weight vector, since it's more efficient than using a queue table to store all the possible states. The feature vector included 11 features in total, including food distance, ghost distance, legal actions, capsule value, distance to enemy Pacman, attacking, which returns a high value if Pacman agent is in enemy half grid, and get safe, which returns a high value if Pacman is threatened. In the Get Safe feature, the Pacman returns to its side if it's carrying more than a threshold amount of food, if a ghost is continuously chasing it, or if the game is in panic time. In other words, if the game is in the final seconds of execution. The default weights of the algorithm was assigned so that Pacman starts to move towards the food positions by assigning a negative weight to the maze distance from Pacman to the food and capsule. If a ghost is detected when in enemy half grid, Pacman avoids it by updating the features by a lower value. If an enemy Pacman is detected in our half grid, the Pacman agent chases the enemy Pacman to eat it.
Hi, I'm Ashley. I'm going to talk about the challenges we faced while implementing the queue learning algorithm and possible ways we could apply those to improve in the future. First, we found that the weights and features were quite sensitive to breakage, I guess. Just minor changes would throw the algorithm out a little. For example, before the Pacman had encountered many other aspects of the map, and it comes in contact with the capsule. If the capsule weight was just a little high, the Pacman would just hover around that area for a bit longer than we'd hoped. On top of that, we thought that possibly creating a non-linear version of the algorithm, so instead of just multiplying the weights and features and then summing them up, we could have experimented with other non-linear ways to combine the two. We also implemented a recursive function in our algorithm which looked n steps ahead to determine how many legal moves there are from our current position. And we found that if n was too high, the algorithm would take too long and return later than the 1 second allowed time.
Hi, I'm Abdul. I implemented value iteration and heuristic search planning in the creation of the Pacman agent. Value iteration based on the Bellman equation was used due to the multiple awards, both positive and negative, that could be mapped onto the state space. The space was created by mapping all available states of the maze in a dictionary. Using the Bellman equation, discounted awards were calculated for each state leading up to the respective award. Furthermore, the policy for each state could be set, which the Pacman agent followed. Enforced hill climbing was also used and interchanged with value iteration in 2 scenarios: at the start of the game and when it was time to score.